And while he gets set up, our next speaker is Sheng Li. He is a research scientist at Google, and he's going to be talking to us about hyperscale hardware optimized neural architecture search.
All right. Thank you, everyone. I'm Sheng from Google. And today, I'm very happy to take us on a small journey about how we co-optimize and co-design ML models for hyperscale hardware. All right, as we all know that this is the era of machine learning. And the machine learning models, the state-of-the-art hardware, and the amount of data that we can access to, they are the driving forces for the recent breakthroughs. Well, it is very difficult, on the other side, it is very difficult to design a high performance and quality machine learning models for the underlying high performance hyperscale hardware. And it has been a multidisciplinary challenge. It requires us to understand the model architectures, the computer architectures, and the system designs. Well, on the other side, the neural architecture search has shown us significant promises in designing the high quality and performance models that rivals the best human design models. And in a nutshell, the NAS employs a controller that samples the model architecture from a search space with more than 10 to the power of 300 or 200 candidates. And then it employs a trainer that trains and evaluates the multi-objective reward, and basically look at each of the models and to see how they perform and what is the quality, and then pick the best one. So the process repeats until the best or Pareto-optimized model from the search space has been selected. However, well, NAS has been showing the significant promises, but there is many challenges hinder the use of NAS to benefit the production-grade ML models on hyperscale hardware accelerators. And in particular, there is challenges from deployment, challenges from efficiency, and challenges from scale. Because of limited time, I cannot go deep into the details about what are the challenges really are, but please feel free to read the paper, or we can talk about it offline. But bottom line is that these challenges, they're preventing us from really benefiting the production models on the hyperscale hardware inside the data centers. And how are we going to solve this problem? And this is our solution. We propose the hyperscale hardware optimized neural architecture search, aka H2O NAS. And inside of the H2O NAS, we have 3 pillars and one foundation. So the first pillar is the search algorithm. We use a massively parallelized one-shot reinforcement learning-based algorithm for hyperscale hardware and leverage the production traffic. The second pillar is objective, and we use a two-phase hybrid performance model and a multi-objective reward function that they are particularly optimized for large-scale deployments. And the next pillar is the search space. We optimize search space for the target hardware and to explore the more than 10 to the power of 300 options in the search space, so that we can get efficient models discovered for very diverse domains on the heterogeneous hardware. And all these pillars, they build upon one foundation, which is we integrate them into a zettaflop scale deployment and running live services, ML services at real time. And now let's deep dive a little bit on the 3 pillars. So the first pillar is the search algorithm. The search algorithm is the heart of the controller, which governs the search process. And the figure looks a little bit intimidating, right? But they are not. Essentially, they only do 2 things. One, the search algorithms learn a policy. The policy determines which is the next model architecture they're gonna look at, and next step. And then the search algorithms also trains the weights. And this part is no difference from any vanilla train job. And there is So we have two figures. On the left-hand side, this is the black and white about the state-of-the-art search algorithms. And on the right side, hand side is what we have optimized for. So the state-of-the-art search algorithms, they learn two things that require, they have one hard requirement. So they need a training data set and a validation data set. The training data set is used to learn the policy, the trained model weights, and the validation data set is to learn the policy to determine the next sample architectures. However, this doesn't work because there is a curse from the production traffic. So we have data privacy and regulations that forbidden us to look at the data and forbid us to store the data and to do post-processing. So we have to do everything in memory. And in-memory processing is so expensive if we want to create two data sets to split the training and validation data. But however, there's also a blessing from the production traffic because there is amount of data from production traffic so huge, so we can afford to use all the data samples once and only once. And then that makes us to propose this unified single step algorithm to learn both architecture choices and the weights, and to achieve the neutral search quality. And with that, we also parallelize this new algorithm, and so that we can run on many hardware in the data centers at the same time. Essentially, your distributed training becomes your distributed new architecture search process. The second pillar is the search objective. Search objective governs the Pareto optimization or the balance between your quality and performance. And usually, we can directly measure the hardware performance, and that will guide our performance objective, but it doesn't work in the production environment because we are searching the model quality during training. Each of the steps is only about 1 to 100 milliseconds, which means we have to get a performance signal at most for every 100 milliseconds. So directly measuring hardware performance is too costly and cannot be afforded. Or we can use an ML model to predict the performance during the search. And traditionally, it works very well in the small settings of the research environment, but it doesn't work in the production environment because we are running a job on hundreds of thousands CPU and GPUs, and we cannot afford to collect data samples on the measurement of 1,000 or million data samples. And what do? We have this hybrid two-phase approach. In the large search space, we take 1 million data samples, the architecture samples. We run through the simulators, so no real job runs. It's very cheap, and we get a simulation results. And the simulation results includes throughput, latency, and memory size. We feed it into a pre-training and we feed it into MLP-based performance model. And then out of the 1 million models, we take about 10 models samples and run them on real hardware. And we measure the performance, real performance, and then we use the measurements to fine-tune the performance model. And then the performance model is able to predict the multi-objective performance metrics that include throughput, latency, and memory sizes. Then we combine the performance model with the performance objective with the quality objective, and then feed it into our single-sided multi-objective reward function. So this reward function is different from previous reward functions in that we do not emphasize it close to the target. We only make sure it cannot go beyond the performance target. If we happen to find the overachiever that they can achieve the same quality but with less cost, we are happy. And then this single-sided multi-objective reward function achieves better Pareto friend compared to the previous double-sided reward function. And then we feed the combined rewards to the H2O-NAS. The final pillar is the search space. And search space is highly dependent on the hardware itself and the model, target model. So here we use the DLRM, the deep learning recommendation model, as an example. And DLRM essentially doing the recommendations for almost everything and anything when we search on the internet, right? We go to the Google, Facebook, Meta, and Amazon. Everything you see, you get recommended is done by the DLRM behind the scenes. And DLRM is a very interesting model architecture. So it has both the dense features and the category also called sparse features. The dense features get processed into a bottom MP layers, and then sparse features go through the embedding table or embedding lookup layers. And then the features get mixed together through the interaction layers, and then finally processed by the top MLP layers before it gets sent to sigmoid for the final click-through with predictions. So inside embedding tables, embedding layers, we have many embedding tables. And each of the embedding table, the height of the embedding table is your vocabulary size. And the width of embedding table is your embedding vector length. And each of the components, they have different requirements or stress the different part on the hardware. For example, the MLP layers are compute bound, and your embedding layers are memory bound, memory bandwidth bound. And we start basic understanding of the model architecture of DLRM. Let's see how we can build the search space for it. So essentially, we search for the vocabulary size of the embedding layers and the width of embedding vectors. We also search for your dimensions and depths of the MLP layers. And because we use weight sharing super network to reduce the cost and reduce the cost for memory sizes and the training steps and everything almost. And so you can see that we use different ways of weight sharing. We use coarse-grained weight sharing when we want to explore different vocabulary size. Essentially, each candidate with different candidates with different vocabulary size, they have a different embedding tables. But we use fine-grained weight sharing to share the vector dimensions. And then with that, I'm going to share a little bit of the specific gears, a little bit for the production results. And this is how we do the end-to-end DLRM optimization on quality and performance on TPU V4 systems. The key point is that we get 10% faster training speed. And I want to emphasize that this is based on a production model that has been running there and optimized for months. And more importantly, this automatically optimizes the model through different system components, the memory bandwidth, the compute, and the interconnect. And it opens the floodgate for full system optimizations across the stack, because now the optimizations on the compute, on the memory, and interconnect can all lead into the final performance results, the improvements. And here is the snapshot for how H2OS performs in the production at scale. In short, we get a 10%, 30% performance gains and about 30% energy efficiency gains with neutral or better quality. And all this has been deployed to Zetaflop ML hardware with live production services with less than 0.03% overhead. Yeah. With that, I'm happy to